Hi, and welcome to the first unit in calculus. Today we're going to touch on just a couple of main topics to get you started. And one of those is limits. And what you see as part of my definition is something you're not going to see in any calculus book. It says that limits are y-value wannabes. And that as the output is going somewhere, or where the output is going, as the input gets really close to some number. So we can think of the y value as the output, as the vertical axis on your graph, as the value of the function. So it's where we would like to see our function go as our input, or x values, or domain, gets really close to some number. And sometimes this number is indeed prohibitive. We can't let denominators be zero. We can't let negatives occur under a radical sign. So sometimes we can just get close and we can't really go there. Sometimes it's safe to go there, but we're going to investigate some various situations. Limits are crucial to the development of the derivative and to the development of the integral, key to their definitions. We don't need to get hung up on them, but we do need to understand them in as plain and simple way as possible so that we can use those definitions to study calculus this semester. I'm going to adjust the camera. So this problem asks you to find the limit of this function, x squared plus 49 over x minus 7, as x approaches 7, and then notice there's a little positive sign there. So the positive sign means it's coming at 7 from the right side. Because if you think of number lines, the positive numbers are on the right and the negative numbers are on the left of 0. So mathematicians, being always, I don't want to say lazy, but taking advantage of shorthand, we write 7 from the right. So as we do that, approaching 7 from the right, you can see that some of the values were chosen 7.5, 7.1, and successfully getting closer and closer to 7. Not letting it equal 7, because if we did, then we'd have 7 minus 7, or 0 in the denominator, and can't have that. Notice what's happening to the output. 210, 994, 9,000, 98,000, and if we kept going 7.00001 as input, we would see that really what's happening is this denominator is getting close to 0, not equaling 0, but getting close. So that when we divide this expression by a teeny tiny little number, we're going to get a very large number. In fact, the answer is indicated positive infinity, meaning a very large number. Here's a graph. Really doesn't make a whole lot of sense as far as labeling it with a function. It's doing some curves and some asymptotic behavior. So I could put a little arrow here indicating it's going to keep on going in both directions. But if we were asked to find, say, the limit as x approaches 3, we could see that there aren't any danger zones. We could just say, whoop, looks like a 0. And safely it is. If we were asked to find the limit of this function, and I probably should write f of x, whatever this crazy function is, as x approaches 0 from the right, we're tooling down here, getting closer to 0, coming from the positive side, and we see our function getting increasingly further down into negative territory. So our answer is going to be, without bound, a negative infinity. Likewise, if we were asked the limit as the function, limit of this function as x approaches 0 from the left, we can see that it's on the other side of the asymptote and going really large. So we're going to write, if there's room for this on the camera, the limit as x approaches 0 from the left is going to be positive infinity. And look at this situation. At -5, we have a filled in dot here and an empty dot here. And suppose these values on the y-axis were -7 and maybe -2. Then it really depends on which direction we come from. If we're approaching 5 from, or excuse me, -5 from this side, our y value wannabe is 7. Oh, excuse me, -7. But if we're approaching the y value, or if we're approaching the x value of -5 from the right side, the positive side, we see our y value wannabe is -2. And it's too hot in here to think. Okay. Let's do this one again. So let's look at limits pictorially with a graph. And here's a crazy kind of graph. And we can see that as x approaches 3, our functional value wants to be 0. And it's safe to do that. There aren't any worries about 0 being, or excuse me, the 3 being a dangerous number. We can't tell if there's any asymptotes or anything. It looks nice, safe, like a part of a polynomial function. Likewise, we have to be careful of that when we look at approaching 0. Because we can see the wings, so to speak, of this function are approaching the line x equals 0 like it were an asymptote. It's scooting down along it. So as we approach 0 from the right, this way, our functional value is getting deeper and deeper into negative territory. So we're going to write negative infinity. As we approach 0 from the negative side, a little negative there, from the left side, we can see that the function is getting very, very large. So positive infinity. Then a very interesting case, as x approaches -5 from 2 different directions, the y values have different wannabes. If you approach -5 from the right, the y value wants to be -2. If you approach -5 from the left, the y value wants to be -7. And if somebody just said, what is the limit as the function approaches -5, you'd have to say that limit does not exist. So limit of the function as x approaches -5 does not exist, because it's different coming this direction and it's different coming that direction. Big gap in the middle there. So you don't know which one to believe. You have to take them separately. You can't group them both together and say there is a limit, because pictorially you can see they're going different places, different y value wannabes. Okay, next. And again, don't make this topic difficult either. A lay definition is can be drawn without lifting the pencil. It's a continuous line. If you had to lift the pencil, you'd have a discontinuity. An example of that is like the early example on limits, where we were worried about the denominator becoming 0. So if we tried to graph this function, I'm calling g of x, we would anticipate that we cannot put a -2 in a denominator, because -2 plus 2 gives us the 0, and we can't have those things undefined. So a discontinuity would occur at -2. And if you graphed it, you'd probably see an asymptote. Don't make this hard. We're going to build upon it when we're going to learn to have to build derivatives. We're going to see that continuity is a really nice thing to have. So we'll spend a lot of time in the realm of polynomials, where things are smooth functions. Next, definition of a derivative. All right, in every calculus book in the whole world, it says that derivative is defined as the limit as h approaches 0 of your functional value, where x used to be inputted. Now we're going to add just a little bit to it. We're going to subtract off the function in its normal state and divide by h. And really, h is, you can say, it's x plus h minus x, where you started from. So that gives you the h in the denominator. What this means pictorially is that we have a function, and here it is at x, and here it is at x plus h. So here's f of x, the output. Here's f of x plus h, the ending output. And our goal is to bring the h closer to 0 so that these points get closer and closer together. And instead of having a secant line that goes from start to finish, we're going to have a tangent line that indicates slope at a point, instantaneous rate of change. So there's our definition. Let's practice with a simple function. So if our function is x squared plus 2, alrighty, we're going to practice the definition of the derivative with a simple function, and we're going to remember that we always have to write the limit as h approaches 0. So we're going to have where the function ended, which was x plus h quantity squared plus 2. So it was x plus just a little bit. That's where we ended. That'll be the functional value. And we're going to subtract the value of the function at the beginning. And then the ending input is that, subtract the beginning input. And it's always end minus beginning. And I always try to think of an analogy with weight. If you gain weight over the holidays, then it's how much you weighed at the end minus your beginning weight divided by the time that elapsed. This is the limit definition of the derivative. So its goal is to bring these 2 points really, really close together so that as h approaches 0, we truly have slope at a point. So let's do the algebra. The derivative is equal to the limit as h approaches 0 of x squared plus 2xh plus h squared plus 2, and I guess we don't really need these anymore. We can just distribute minus x squared minus 2 all over h. Now you can see that some of these are going to collapse. X squared and minus x squared, positive 2 and minus 2. So to clean up, we're going to have the limit as h approaches 0 of 2xh plus h squared all over h. So we're messy. And this looks a little bit like gibberish right now, but see where this is going to go. We're going to next factor out an h. Our derivative is equal to the limit as h approaches 0 of, factoring out an h, 2x plus h. And then, let's get the red out again. We can see that h over h is just 1. Don't need to write that. So, getting closer. Limit as h approaches 0 of 2x plus h. Now, notice no denominators to worry about. So we could actually let this get so close to 0, it could be 0. No danger. Equals, we're going to let it slide to 0, and we're going to get 2x. Alrighty, this says, by the limit definition of the derivative is equal to 2x. So we can pick an x from anywhere on the graph, put it in here, and we can find the slope that exists. In other words, if we drew a series of tangent lines, their slopes would be given to us by this, depending upon where we are what kind of x values we're inputting. Not so bad.